Good afternoon, everyone. Thank you for joining us. This is Katie Raleigh, librarian at the NOAA Central Library. We're very happy to host another in our NOAA Innovators series. A little housekeeping to start us off. If you do have questions during the webinar, please place them in the question panel and we will try and answer them at the end of the presentation. If your question is not answered, we will pass that on to the presenter afterwards and they will connect with you offline. If there are any issues with your sound or video, please try logging off and then logging back in. That usually clears up about 90% of the problems. If you're still having issues, please chat with me and I will try and solve those for you. And with that, I'm going to turn it over to Tiffany House.
Thanks, Katie. Good afternoon. Thanks for joining us today, everyone on the line. My name is Tiffany House, and I am the commercialization specialist for the NOAA SBIR program, which stands for the Small Business Innovation Research Program. NOAA's SBIR program provides competition-based awards to small companies for research and development to transform their innovative ideas into commercial products. All SBIR proposals must directly benefit the NOAA mission and have excellent commercial potential in order to be successful. Prescient Weather successfully completed a Phase II NOAA SBIR in 2018, focusing on subseasonal prediction of impact variables of importance to the energy industry. The research created an operational multi-model subseasonal forecast method that was then used to predict impact variables 3 to 5 weeks in advance. Dr. Dutton is the CEO of Prescient Weather. Dutton holds a PhD in Meteorology and MBA from the Pennsylvania State University. He has served in multiple roles at well-known companies. In his current role at Prescient Weather, Dr. Dutton's primary focus is on marketing and sales to widely distribute the fantastic S2S science to product activities of the company. Ladies and gentlemen, it is my pleasure to introduce Dr. Dutton.
Great, Tiffany. Thank you very much for the introduction. I greatly appreciate it, and I appreciate the opportunity to discuss the research and development work that was supported by the NOAA SBIR. And so, I labeled the title of the presentation as Subseasonal Forecasting and Emerging Capability of the U.S. Weather Enterprise, in part because subseasonal forecasting certainly has become a focus of the weather enterprise. And as Tiffany mentioned, the actual title of our SBIR proposal was Probabilities of Business Impact Variables from CFS version 2 Ensemble. So that's the Climate Forecast System version 2 ensembles. And so really the primary goal of this SBIR was to transform subseasonal forecast, ensemble forecasts into probability forecasts of impact variables that are important to the energy industry. So just a little bit of background on the company. Prescient Weather was actually founded in 2009. And from the founding, there's been an 11-year history of producing Crop Profit, which is a US-focused corn and soybean yield forecasting system. And then the World Climate Service is a product that actually was in existence before the founding of Prescient Weather, but came to the party, as it were. And the World Climate Service is really two things. It's a tool set of calibrated ensemble dynamical forecasts, of analog analysis, and then statistical forecasts as well in the subseasonal and seasonal time frame. And it's designed to enable industrial meteorologists to improve their long-range forecasts and the communication of risk that they have to their internal constituencies. It is also then digital feeds of the dynamical seasonal forecasts, which are designed to enable quantification and integration into decision-making systems. So our goal at Prescient Weather is to create quantitative guidance for weather and climate-related decisions based on the best science available. So what we're trying to do is both research and entrain the latest science available in subseasonal and seasonal forecasting and integrate them into our product. So a lot of the focus on subseasonal forecast has come about in part because of the U.S. Weather Act. So the U.S. Weather Act became law on April 18th, 2017, and it includes a number of different requirements for the United States to make significant progress in weather forecasting technology and forecasting improvements. And it includes a specific section on seasonal and subseasonal forecast innovation. And so a lot of the activity that has occurred around subseasonal forecasting is engendered by the fact that the U.S. Weather Act exists. And within the Weather Act, there is specific language around the fact that the Act should also support non-federal weather research community activities, including both the academic and the private sector. And so we see some of this work that we've done under this SBIR really as supporting some of the mission of the U.S. Weather Act of making subseasonal forecasts not only better, but also applicable to real world problems. And so within the weather enterprise, which is generally considered to be the government agencies involved, the academic sector, and then the private sector as well, there has been a considerable focus around subseasonal forecasting. At least from my view, the government and the academic sectors are participating in improving subseasonal forecasts through the SubX experiment and the NMME, which is the multi-model ensemble program for seasonal forecasting. And so those are federally funded projects, and there's multiple research efforts associated with them. And there's quite a bit of work occurring at the Climate Prediction Center as well around improving 3 to 4 week forecasts and other seasonal forecasting and subseasonal forecasting capabilities. And then within the private sector, there are several companies, including Prescient Weather, that are developing products specifically focused on the subseasonal timescale. So a few years ago, the National Academies of Science published a report on and made suggestions around strategies for improving seasonal to subseasonal forecasts. And so I used this graphic as an opportunity to sort of define what a subseasonal to seasonal forecast is. And so this graphic depicts that there's different types of forecasts, everything from real-time forecasting for severe weather warnings and alert creation, to the other end of the timescale of climate projections, which is trying to model and understand what future climates are likely going to be. Subseasonal forecasting fits in this time frame of beyond 2 weeks, but less than seasonal forecasting. In our practical application in the business, subseasonal forecasting is in the range of 3 to 5 weeks, which is based on skill. And then I tend to call seasonal forecasting, once we get into months and seasons, I tend to consider seasonal forecasts because of the slight difference in methodology used between the two. When I talk with customers, I usually show this graphic, and this graphic is designed to talk about the fact that weather forecasting is really an initial condition problem, and it's the initial conditions that are most important when looking at weather forecast information. Whereas when we look at, say, seasonal forecasts and longer term forecasts or projections, you're really talking about the boundary conditions of the Earth atmosphere system. And subseasonal forecasting, this range of 3 weeks to maybe 1 month, is in this really difficult position where both initial conditions can be important and boundary conditions can be important as well. And so there's this really interesting research occurring to try to understand the sources of predictability in the subseasonal time frame. And so the result is that because the subseasonal forecasting and seasonal forecasting is more of a boundary condition and a climate problem, it's necessary to think in terms of probabilistic forecasting. So if we took for some position on Earth a long time series of monthly average temperatures, and we looked at the distribution of those temperatures, say over a month, many years over of monthly average temperatures, we'd see that roughly speaking, the temperature is normally distributed. And so one of the things that we've done in the concept of our product is we consider tercile forecasts, in which we're creating forecasts of temperatures or impact variables in terms of below normal, normal, and above normal, which is simply the 33.3% section of each of the distributions. So to forecast the future in terms of weather forecasting and climate forecasting, the science uses ensemble dynamical forecasts. And so the ensemble is multiple realizations of a possible future. And that possible future is determined by generally varying the initial conditions of the model run. And so we have multiple different realizations of the possible future, and that future has to be analyzed in terms of a probabilistic context as well. So the science tells us that it's impossible to pick out a particular temperature 30 days into the future, but it also tells us that it's possible to use probabilities to understand what the distribution of the temperature might be averaged over a certain time period. So using this distribution as an example, when we're forecasting in the long range, in the weekly and monthly time frame, we're really forecasting the shift of that distribution. So in the example I've shown here, there is an example predicted climate distribution that shows that there's a 50% chance of below normal temperatures, and then a 50% chance of the temperatures occurring in the normal or above normal time frame. And in fact, in this case, we're showing a very small probability of above normal temperatures in general. So the science of a subseasonal or a seasonal forecast from dynamical models is to try to understand what the shift in this distribution is by analyzing the forecasts made from the ensemble dynamical models. And so the science goes even further, in which value is created through a forecast calibration process. So it turns out creating a diagram of the calibration process is quite difficult. So I apologize if this isn't clear. But in the calibration process, we have what are called reforecast time series, which is the ensemble models are run back through time using the initial conditions of a particular date. And we generally have between 17 and 20 years of reforecast data of, say, the climate forecast system ensemble forecast. And we compare each of those forecasts to the observed conditions that occurred. So we have roughly 20 years of ensemble reforecast data. We have roughly 20 years of, say, weekly average temperature data. And the calibration process then minimizes the difference between the cumulative forecast probability distributions and the observed probability distributions. So it is literally an optimization problem in which we're minimizing the difference between two parameters. And through that calibration process, then we gain a better understanding of the probabilities of the future outcomes. And it's really what we have found in our productization of the technology is that the calibration process is really critical to creating customer value. And we'll talk about that in a little bit. So the result then is you end up with probabilities of above normal, normal, and below normal conditions. So much of the material that you see publicly available tends to be maps of anomalies in, say, the 10 to 15 day forecast or the 3-week forecast. And that is not what I'm depicting here. What I'm depicting here is this is a map of the shifts of the probabilities. So the areas in red, the areas in deep red are 60 to 70 or even 70 to 80% chance of above normal probabilities. In this case, 3 weeks in advance. I happen to be showing Europe in this case because there's a pretty strong Arctic oscillation signal this winter, and the probabilities are quite strong in the 3-week forecast. So the subject of our SBIR was forecasting impact variables of importance to the energy industry. And so I show here an example of a heating degree day forecast. So in this case, it's a week 2 forecast of heating degree days in which we see generally higher probabilities of above normal heating degree days, meaning generally colder than normal. And we see below normal probabilities of below normal heating degree days. And so heating degree days is an important parameter in the energy industry because it's used to model energy consumption. So there's heating degree days and cooling degree days and various ways of weighting them based on population or region. And it's a very important parameter. And so being able to forecast heating degree days in the long lead allows for better planning. It allows for improved speculation, and it's a critical variable for the industry. The rise of renewable energies, both solar and wind, also creates opportunities for wind speed and solar intensity forecasts in the subseasonal timeframe to provide value as well. So under the SBIR, we work through understanding subseasonal forecasts for wind speeds. And as an example, again, another example here is a week 3 forecast. So that's a forecast with 3-week lead time for wind speeds during the week measured the 27th of February to the 4th of March. And again, the idea then is that the calibration process allows us to better understand the probabilities of the likelihood of, say, below normal wind speeds, as we're showing here in the South Central United States. So this element of forecasting impact variables is one of the significant outcomes of the work done under the SBIR. We also have done work towards integrating a 30-day based forecast from the climate forecast system into our crop profit yield forecast system. So in the agriculture industry, there's an awful lot of information that discusses what the impact of weather is on crops, but they never quantify it. And so we have a crop yield forecast model that quantifies the impact that weather has on yields. And because we have that relationship, we can then apply forecast information as well and quantify the implied impact from a forecast. So this is an example then of a 30-day outlook in terms of 30 days into the future. The yield forecast should be a specific value as well. One of the things that emerges, particularly in the weekly time frame, so 3 weeks and 4 weeks in advance, is the concept of forecasts of opportunity. So in the process of calibration, you are working towards understanding and making sure that the probabilities that you forecast an event, say above or below normal temperatures, occurs in the observed history as often as you forecast it. So what I'm showing here, this happens to be it's a forecast of below normal temperatures that occurred last March for northern India. So the top graph, the top chart is the probability forecast in terms of the probabilities of below normal and above normal temperatures. So the deeper the blue, the higher the probability. The deeper the red, the higher the probability of above normal temperatures. And then the bottom is the observed climatology, which is to say this is what happened for the same week that we forecasted 3 weeks in advance. And we can see that the cooler than average temperatures that occurred fairly closely matches the prediction of below normal probabilities of cooler temperatures. And so this is a forecast of opportunity, meaning that the ensemble models in this case were tightly concentrated in their forecasts, and it was easy in effect. It was a forecast of opportunity to pick out the colder than normal forecast. So it's important to communicate the forecast as well. So I use this as an example of what I call a tweet of opportunity. And so again, communication of the forecast is important as well. And so we use this particular outcome as an opportunity to demonstrate that forecasts in the long range are possible as well. And so to drive into this a little bit further, we can get into some formal results. So what I'm showing here is probabilistic forecast verification of week 3 forecasts over Europe and over North America, in which what we are looking at is it's the fraction of forecasts verifying as correct. So the idea is that we have over North America, we have a long history from the reforecast data of forecasts of below normal, normal, and above normal temperatures. And we can use then the observational record to understand if that forecast was correct, meaning if we forecasted the right tercile, so the right category of below normal, normal, or above normal. And what we see is when the probability forecast was at least 33% in December, January, and February, the climate forecast system calibrated result forecasted about 45% correct, forecasted the right tercile about 45% of the time. We have access to the ECMWF extended ensemble runs, and so that's about 48% of the time. And then a multi-model ensemble of the two was slightly better. If we look at probabilities of at least 50% or greater, in wintertime, we see that the CFS verified about 58% of the time, the ECMWF 62% of the time, and then the multi-model ensemble verifies that about 68% of the time. So I just want to take a step back and just think about this for a second. So this is a 3-week forecast of temperature over land, and it verifies correct 70% of the time. I happen to think that's quite remarkable. The challenge, though, is that the frequency with which the forecasts occur at 50% is relatively infrequent. And it gets as you go from week 3 to week 4 to week 5 and week 6, the probability of highly concentrated forecasts, let's say probabilities of 60 or 70%, become very infrequent. And so that's why it's a forecast of opportunity, because it doesn't happen day in and day out. But when it does happen, there's valuable information to be had within the information. And then the forecast of opportunity concept is also applicable in the seasonal timescale. So within the World Climate Service, we produce a subjective seasonal forecast for North America and Europe. Subjective means that in this case it is a human interpreted forecast, and the human interpreted forecast leverages the dynamical models, the analog tools, and the statistical tools. But there are times when high confidence forecasts can be made. And so as an example, the forecast for the summer of 2018 in Europe was a forecast of generally warmer than average temperatures, shown on the left, and we can see that on the right-hand side, that forecast generally verified as well. So the forecast of opportunity concept is pretty important for the application of subseasonal and seasonal forecasts. There's quite a lot of work going into understanding strategies for climate adaptation and climate resilience as we continue to march forward in time. And one of the things I've been interested to see is that the concept of early warning systems, in a very simplified sense, are basically subseasonal forecasts of precipitation and temperature events. So extreme temperature and extreme temperature events. So some of the work that we did in the SBIR was trying to understand the degree to which the climate forecast system can forecast extreme events. So we tested something that we ended up calling the Extreme Potentials Index, and it's a modified version of a technique used at the European Center for Medium Range Weather Prediction to understand extremes in ensemble forecasts. And we also looked at real-time forecasting of the probabilities of droughts. And so the idea in both of these cases is that the skill of the event is really important. And so the maps that we're looking at are both an indication of the shifts of probabilities of severe or disruptive events, but they're also masked by skill. And so areas that are white either have no skill for the event, or the ensembles had no signal as well. And so we see in terms of the application of subseasonal forecasting, moving towards forecasts of significant and disruptive events will be an important application moving forward, and really provide value both to businesses as well as in the humanitarian frame of trying to improve climate resilience and climate adaptation. And so along those lines, one of the things that we sort of anecdotally see is that particularly in the warm months of regions of the world that already experience pretty extreme temperatures, we've seen that when there are probabilities of increased, when there's higher probabilities of above normal temperatures, extreme events tend to happen. And so this is, in this case, this is an example of a forecast of just above normal temperatures, right? So higher probabilities of above normal temperatures, and the result was record-breaking warmth again in India. But the idea then is that certainly there's signal and there's information in the subseasonal forecast for extreme events as well. So part of what we did as well was not only sort of work through the methodology to create the forecast, but we also understood that application of the forecast is really important. So the best forecast in the world doesn't really matter if you're unable to apply it. So part of what we did within the SBIR was work through some of the logic and the techniques and the science behind the actual forecast application. And so we explored the possibilities of using a financial business model that gives you outcomes, sort of financial outcomes for adverse or beneficial climate events, along with the historical forecast performance of, say, the CFS, and trying then to figure out a model that would allow you to have expected financial performance based on the benefits of using seasonal or subseasonal forecasts in your decision-making process. And so I think we all know that there's many things that are impacted by weather. There's many business outcomes that are impacted by weather, and a couple are listed here on this page. But what we tried to work through was an understanding of how do you take a how do you take a forecast like a subseasonal forecast that can be skillful at times, and that can be very skillful at times, and use that in a business making context to try to answer important questions in the business context as well. Whoops. And so in terms of the application of subseasonal forecasts in the work that we've done and in the discussions we've had with potential customers, subseasonal forecasts will certainly have benefit in energy, insurance, agriculture, transportation, retail, water resource management, human health, emergency management. This is a partial list and certainly not an extensive list, but there's certainly opportunities for subseasonal forecasts to be used in a wide range of applications. What we see occurring is that many businesses and many people are quite familiar with the 3-day forecast, the 7-day forecast, 10, 14-day forecast, weather forecast, but they're looking beyond that in trying to gain operational improvements or competitive advantage in their business. And they're looking for information beyond the range of the traditional weather forecast. And subseasonal forecast is going to be the answer. But the key then is that it has to be, the information has to be made available in a way that enables the business application. And so the purpose of the SBIR is to provide research opportunities that enable commercialization as well. And so the World Climate Service today is focused on energy companies. And believe it or not, it's really focused on meteorologists that sit on energy trading desks. So as I mentioned, the World Climate Service is a tool set to enable improved long lead forecasts. And so our customers there include some of the world's largest electric utilities based in the US and Europe. It includes energy trading desks that are based in the United States and Europe, and it includes hedge funds. And so that is the primary use. We're also finding that we're having some success in the insurance space, and in particular with insurance companies that are offering weather insurance contracts or helping companies hedge their weather-related risk. And they're using the subseasonal and the seasonal forecast information to understand what the risk of their portfolio is, to see if they need to take a potential corrective action or somehow hedge the risk that exists within their portfolio. We're also seeing some interest in the crop insurance space, where again, it's weather impacts the payout ratio associated with crop insurance. And so they're trying to use long-range forecasts to try to understand the risk. We are doing work with a company called Global Parametrics, which is it's a company funded by the German and the British government, and they're particularly focused on finding and creating pathways to hedge weather-related risk as well. And so they're leveraging some of the forecast expertise that we have to enable risk transfer for weather-related risks. We are also seeking opportunities in other segments, and two that we're particularly proud of is the Danish Meteorological Institute, which is the National Weather Service of Denmark, is using the World Climate Service in their subseasonal forecast preparation. And so the calibrated dynamical forecasts that we developed as part of the SBIR are certainly critical, but really the entire tool set that we're offering is also important as well. And folks may have seen in the news that there's a very significant locust outbreak occurring in Africa this winter. And so it turns out that the UN Food and Agriculture Organization Locust Monitoring Center uses the World Climate Service to try to get, they use it for long lead forecasting of precipitation events to try to understand if there is a higher risk than normal of an outbreak about to occur. And then finally, we already mentioned we are trying to integrate some of the subseasonal forecast information into our own product, Crop Profit, to try to improve the information in that product as well. The benefits of the SBIR also extend to the academic sector. So as an example, there is a class this year at Penn State University in that they're using World Climate Service as a forecast tool in a class that's focused on weather-based commodity risks. We just entered into a collaboration with the Alaska Center for Climate Assessment and Policy at the University of Alaska Fairbanks, which interestingly enough is a climate program office funded RISA. And we're exploring being an operational platform for the heat index forecasting capabilities of Dr. Ventizelos at the University of Maryland. And so the capabilities that we're creating are creating a usable platform for the analysis and communication of climate and weather related risks. And so finally, I guess I want to talk overall about the benefits of the SBIR platform. So what I'm showing here is calibrated and uncalibrated January lead 3 results from data downloaded from the SubX program. And what we see is the uncalibrated ensemble forecast tends to overpredict the probabilities. But when you calibrate the results, you can end up with a forecast fairly close to that 1-to-1 line. So this is called a reliability diagram. And the idea is that in an ideal world, the forecast events, the probability of the events that you're forecasting fall along that black line. And the calibration process is what helps you tune your forecast to try to get the probabilities correct. And so the idea then is that the calibration of the impact variables allows you to develop reliable forecasts so that the end users can understand the risk of the decisions that they are making that are weather impacted. And that's a really important part and an outcome of the SBIR work. The other element is that forecasts of opportunities create situations in which the subseasonal forecast can really derive value for customers. So if customers have a risk to extreme events, and I don't mean extreme events in the weather sense, I mean extreme probabilities like, let's say an electric utility has a risk of warmer than normal temperatures, they can work towards hedging that risk by understanding what the forecast is. And so if we go further, we can look at this is the same fraction of forecast verifying as correct that I used earlier. And we see that the benefits of calibration, whether it be a temperature forecast or an energy impact variable such as heating degree days or wind speed, the benefits of calibration are really, really an important aspect of the forecast. And so that end-to-end process that we developed of processing the dynamical models, conducting the calibration, forecasting the impact variables, and making them available in formats and contexts that allow customers to make decisions is really an important outcome of the overall SBIR. And the way I see it is that the weather enterprise is really focused on conducting the research that is required to make subseasonal forecasts valuable and useful. And then it's companies like ours that help answering specific questions that customers have. And so the SBIR not only supported the research, but is also really helping to drive the application of subseasonal forecasts within primarily the private sector, but there doesn't necessarily need to be limited to applications within the private sector as well. And that's all I have. Thanks everyone for listening. You can learn more at worldclimateservice.com if you want to. Thanks very much.
Awesome. Thank you so much, Dr. Dutton. We do have a few questions online. And so I'm going to kick that off with our first question. How skillful is the week 3 forecast and how much risk the user communicated? I'm committed. I'm not sure what this person wrote here. So how skillful is the week 3 forecast?
Sure.
And then how much risk the user is committed to take with low skill predictions?
Sure. So I guess I have 2 comments then. One comment then is, I guess the best answer I have right off the top of my head is this chart. So how skillful is the week 3 forecast? So the week 3 forecast, when the probabilities in the forecast are quite high, they verify pretty close to the probabilities suggested by the forecast. And I'll say that's the specific role of calibration. So the role of calibration is that if you say there's an above normal temperature event occurring with a 70% forecast probability, that it should occur observationally 70% of the time. And again, roughly speaking, we find that that is true. And so that's why we talk about forecasts of opportunity. When the probabilities are high, the forecast is much more reliable in terms of your ability to make decisions from it. So then to answer the question about low probability forecasts, I'll go to one of our forecasts as an example. So just using this map as an example, The areas in red are highlighting probabilities of above normal temperatures. The areas in blue are highlighting temperatures of below normal temperatures. The areas in white mean one of two possibilities. One is that the ensembles had no particular spread in either direction. And so you can see on our probability scale, for instance, we even highlight probabilities of normal conditions. But there's an area of white here, which is where the ensemble spread, there's no information in the ensemble spread to make a decision. The other interpretation of the regions of white is that the model had no skill in that lead time for that variable for that geography. And so the process of calibration is that when there's no other information, the forecast is a forecast of climatology, meaning the probabilities of climatology, which in temperature would mean 33% below normal, 33% normal, and 33% above normal. And so the skill you could expect would be equal chances that either tercile are going to occur.
Great, thank you. I'm going to ask our next question. So in terms of further improvements, where do you see a need? Is it in more observations, and what types of observations, or is it in more computing power for this process?
Yeah, I guess that's a great question. I will give you a short-term perspective and one that is easily solvable with more computing power. One of the limitations that certainly we experience in our ability to train a calibration is that a majority of the reforecasts are never longer than 20 years long. And I'm sure, again, it's primarily a computing power problem. But basically, the longer reforecast data that you have from multiple models, the better opportunity there is to train the model. So I would say in the very short term, a very piece of low-hanging fruit for improvement of the forecast is going to be to have longer reforecasts.
Great, thank you. Next question. What kind of data would help to improve overall accuracy of the forecasts?
Well, interestingly, I will say that we're actually engaged on an effort right now to understand optimization of the subseasonal forecast. And it's questions like, at what number of models do you get a diminishing return on improvements in skill, right? If you have a two-model multi-model ensemble and you add a third, are you going to improve skill? If you have 15 and you add a 16th, are you going to add skill? So again, it may be model data, but there certainly is going to be a diminishing return at some point. I actually think in terms of observational data, we are very heavy users of reanalysis data. So call it gridded observational data, even though that's not quite the right description. So I'm not sure it would be improved observational data per se. Certainly data around the models will be really what's driving the forecast. So it's probably something related to modeling.
Great, thank you. The next question is the calibration done by Prescient Weather the same as the bias correction for sub-X and NMME forecasts using the same hindcast database?
No, our calibration is a proprietary system.
Perfect. Thank you. The next question. The CFS runs 4 times a day. Were you able to notice how much flip-flopping happens from run to run as one leads up to a week 3 forecast? Do the forecasts tend to converge towards big events or not?
Great question. We have not studied the flip-flop issue. I will say that for every forecast that we create, meaning every forecast that we release, we're doing a skill optimization and trying to optimize the number of ensemble runs to include in the forecast, which is dependent by lead time and variable in geography. So we haven't actually studied the flip-flop issue.
Okay. And that second question, I'm not sure if that answers it. Does the forecast tend to converge towards big events or not?
Does it tend to converge towards big events? Well, I guess our probability forecast in event, it is in effect a forecast of whether it's converging or not. So if we end up with a 70% probability 3 weeks in advance of above normal temperatures, then the solution is converging.
Okay, thank you. One more question. The National Weather Service CPC currently lumps together weeks 3 and 4 in their CFS V2 based forecasts. Do you find more skill in separating out these two?
I don't know the specific answer, which is I don't have the science in front of me. In general, in meteorology and climate science, anytime you average over space and time, you increase skill. So I would imagine that averaging together week 3 and week 4, you're increasing the skill of the forecast.
Great. Okay, we do have one last question. It's a little more complex, so please forgive all of the acronyms I'm going to say.
Sure.
So some of the verification results that you shared suggested that your multimodal approach improves the reliability of, say, 2TM over raw CFS V2 or ECMWF. Do you feel that for the range of error in these forecasts, do you have a feel for the range of error? Does the multi-model approach reduce these?
Certainly, I will say ensemble theories suggest that multi-model approaches create more accurate forecasts. So I don't have information off the top of my head that would suggest what the error reduction is by, say, looking at individually the CFS or individually the CFS, the ECMWF, and then combining the two together into a multi-model ensemble. The error is certainly reduced, as indicated by the graphics that I showed, but and I guess that provides a quantification of it as well. Again, I don't, off the top of my head, the answer is yes, but I need to look into the details to know what the numbers are.
Great, thank you, Dr. Dutton. I believe that is the end of our questions. If anyone does have anything else, please put it in the question panel now, and we'll try and grab those before we wrap up. But I think that's it. Tiffany, do you have anything you would like to add at the end here?
No questions from me. I was trying to take it off of mute, sorry.
No, you're fine. Okay, if that is it, thank you everyone for joining us, and this has been recorded, so if you want to share this later on, the library will be posting it on our YouTube channel. And I will give everyone back about 15 minutes of their lunch hour. Thank you so much for joining us.
Great, thank you everyone.
Thank you.